Imagine a magic box. You drop a number in the top, a gear turns inside, and a new number pops out the bottom. That box is a function. A function is just a rule that takes an input and gives back exactly one output. For every number you put in, you get one number out, never 2 or 0. We give the function a name, often just a letter like f, and we write f of x to mean the output when the input is x. For example, if the rule is add 3, we write f of x equals x plus 3. The x is the input, the thing you drop in, the whole expression f of x is the output you get back. Why do we care about a box that changes numbers? Because the world is full of relationships where one thing depends on another. If you know how many hours you work, a function tells you your pay. If you know the side of a square, a function gives its area. A function turns a question, what is the input, into a precise answer. In calculus, everything we do, rates of change, slopes, areas under curves, is built on functions. They are the basic building blocks. If you can think of a process as an input-output machine, you can use all the tools of calculus to understand it deeply. This course will take that simple machine idea and stretch it, flip it, and zoom in on it to solve real problems. Let's open the machine and see its rules. Not every number can always go in. The set of all allowed inputs is called the domain. Think of it as the menus of numbers the machine accepts. The set of all outputs it can actually produce is called the range. For our simple rule f of x equals x plus 3, you can put any real number in, -2, 0, pi, 100, so the domain is all real numbers. And you can get any real number out, so the range is also all real numbers. But some machines are picky. If the rule was 1 over x, the domain would exclude 0, because dividing by 0 breaks the machine. We'll see many such rules. The notation f of x is just a compact way to say the output of the function f when the input is x. The letter f names the rule, and the parentheses hold the input. Let's use our machine on a real problem. You're traveling and the weather app says it's 20 degrees Celsius. What is that in Fahrenheit? The conversion is a perfect function. The input is the Celsius temperature, the output is Fahrenheit. The rule, discovered by measurement long ago, is f equals 9/5 times c plus 32. Here, c is our input variable, like x. So we just feed 20 into the machine. 9/5 times 20 is 36, plus 32 gives 68. So 20 degrees Celsius is 68 degrees Fahrenheit. Notice the function gave exactly one output for our input. The domain here is all Celsius temperatures from absolute 0 upward, and the range is the corresponding Fahrenheit values. Every time you use a formula like this, you're using a function. The whole idea is, a function is a dependable rule that turns an input into exactly one output, letting us model and predict the world. You already know a function is like a machine. You feed it an input, it follows a rule, and it gives you an output. Now we need a way to write that down without drawing the machine every time. The notation we use is f of x, written f, open parenthesis, x, close parenthesis. The letter f is just the name of the function, it stands for the whole rule. The x inside the parentheses is the input placeholder. It says, whatever you put in here, that's what the rule will act on. So f of x is not f times x, it's the function f, applied to the input x. Think of the parentheses as the mouth of the machine, waiting to be fed. Why do we bother with this f of x notation? Because a function is a general rule that works for any input. We don't want to write a new sentence for every single number. If I say the rule is square the input and add 1, that's a mouthful. But if I write f of x equals x squared plus 1, I've captured the whole rule in one line. Now I can ask, what happens when the input is 2? What about when it's a? What about when it's x plus h? The notation lets us answer all those questions just by replacing x with whatever we're curious about. In calculus, you'll constantly ask what happens to the function when the input changes by a tiny bit. And f of x plus h is exactly how you set that up. This is the language that lets you talk about change. Here's the only rule you need. To evaluate a function, take the expression inside the parentheses and put it wherever you see x in the rule. It's a literal copy and paste. Let's say our function is f of x equals x squared plus 1. To find f of 2, we replace every x with 2. That gives us 2 squared plus 1, which is 4 plus 1, or 5. To find f of a, we replace x with a, giving a squared plus 1. It looks the same, just with an a instead of a number. Now the big one for calculus, f of x plus h. We take the whole chunk x plus h and put it in the parentheses. That means we square the entire quantity x plus h, then add 1. So f of x plus h is the quantity x plus h squared, plus 1. Let's make this concrete. Imagine you're walking at a steady speed of 5 meters per second. The distance you cover is a function of time. We can write that as f of t equals 5t, where t is the time in seconds. What's the distance after 2 seconds? We evaluate f of 2, replace t with 2, giving 5 times 2, which is 10 meters. Now here's a question that feels like calculus. How far do you travel in the 1 second interval starting at time t? That interval goes from time t to time t plus 1. The distance at the end is f of t plus 1. We evaluate by replacing t with the whole chunk t plus 1, 5 times the quantity t plus 1. That's 5t plus 5 meters. Notice we didn't just write 5t plus 1, the parentheses made us multiply the whole thing by 5. Imagine you have 2 function machines. The first one, called g, takes a number and does something to it, maybe adds 3. The second machine, called f, takes whatever comes out and does its own thing, maybe squares the number. Now, instead of you carrying the output from g over to f by hand, we connect them with a pipe. The output of g drops straight into the input hopper of f. That's exactly what composition is, feeding the output of one function into the input of another. We write this as f composed with g, with a little circle between them. The notation f of g of x means you first put x into g, get g of x, and then feed that result into f. The little circle is the pipe. Why would we want to chain functions together like this? Because the world is full of step-by-step processes. Think about buying a shirt on sale. The store applies a 20% discount first, and then charges 8% tax on the reduced price. That's 2 functions in a row, discount then tax. Composition lets us wrap that whole 2-step process into a single function. In calculus, when we later learn the chain rule, you'll see that almost every interesting function is built by composing simpler ones. If you can break a complicated action into a chain of simple machines, you can understand it, graph it, and eventually find its rate of change. Composition is the glue that lets us build big ideas from small, manageable pieces. The most important thing to get right is the order. Even though we read f composed with g from left to right, the action goes from right to left. The function closest to the x, which is g, acts first. Think of it like putting on socks and shoes. You put socks on first, then shoes. In our notation, shoes composed with socks means socks first. To evaluate a composition, always work from the inside out. Let's take a concrete example. Suppose f of x is x squared, and g of x is x plus 3. To find f of g of 2, we start inside the parentheses. G of 2 is 2 plus 3, which is 5. Then we take that 5 and feed it into f. F of 5 is 5 squared, which is 25. So f of g of 2 equals 25. Let's solve a real problem using composition. Imagine a circular puddle of water that's spreading. Its radius grows over time. Suppose the radius at time t seconds is given by r of t equals 2t centimeters. So after 1 second, the radius is 2 centimeters, after 3 seconds, it's 6 centimeters. Now, we want a function that gives the puddle's area directly from time. We already know the area of a circle from its radius, a of r equals pi r squared. That's a function. To get area from time, we compose them, are composed with r of t. We feed the radius function into the area function. That means we replace r in the area formula with 2t. So a of r of t equals pi times the quantity 2t squared. 2t squared is 4t squared, so the area is 4 pi t squared. At t equals 3 seconds, the area is 4 pi times 9, which is 36 pi square centimeters. You already know that a function is like a machine. You drop in an input, and it spits out an output. And you know that composition means putting one function inside another, working inside out. Now we're going to build the actual formula for that combined machine. That means taking the entire expression for the inner function and substituting it wherever the outer function has an x. It's like taking a whole little machine and sliding it into the input slot of the bigger machine. Instead of just feeding in a single number, we're feeding in a whole algebraic rule. Why build a formula instead of just doing it number by number? Because in the real world, many processes happen in steps. Imagine a factory. One machine adds a coating, and the next machine bakes it. The final product depends on the order. If you bake first and then add the coating, you get a burnt mess. Algebraically, f composed with g is generally not the same as g composed with f. Building the formula lets you see that difference clearly. And in calculus, when you learn the chain rule for derivatives, you absolutely must be able to write the composite function's formula to take it apart again. This is the essential first step. Let's derive the formula step by step. We start with our two functions, f of x equals x squared, and g of x equals x plus 1. To build f of g of x, first look at the outer function, f. It says to take the input and square it. We can write that as f of something equals that something squared. Now, the inner function is g of x, which is x plus 1. So we take that entire x plus 1 and drop it right into the empty parentheses of f. That gives us f of g of x equals the quantity x plus 1 squared. Now let's do it the other way, g of f of x. The outer function is now g, which says take the input and add 1. So g of something equals that something plus 1. The inner function is f of x, which is x squared. Drop x squared into the parentheses, and we get x squared plus 1. Let's solve a concrete everyday problem to see why order matters so much. Imagine a store has a sale, 20% off everything, and then you have to pay a 5% sales tax. The final price depends on whether the discount or the tax is applied first. Let the original price be $p. The discount function, d of p, takes 20% off, so you pay 80% of the price, d of p equals 0.8p. The tax function, t of p, adds 5%, so you pay 105%, t of p equals 1.05p. If the discount is applied first, we compute t of d of p. We substitute d of p, which is 0.8p, into the tax function. That gives us 1.05 times 0.8p, which equals 0.84p. You pay 84% of the original price. When we build a composite function f of g of x, we feed x into the inner function g first, then take that output and feed it into the outer function f. The domain of the composite is not just the domain of the final simplified formula. It is the set of all x that can successfully travel through both machines without breaking any rules. Think of it as a two-stage filter. First, x must be a valid input for g. Then, the output g of x must be a valid input for f. Only the x values that pass both checks make it into the domain of the composite. If x fails either stage, it is kicked out. Why do we need this two-stage check? Because the simplified formula can lie to you. Suppose g of x is x squared, and f of x is the square root of x. If we compose them, f of g of x becomes the square root of x squared, which simplifies to the absolute value of x. The simplified expression accepts any real number. But let us trace the journey. The inner function g is x squared. Its domain is all real numbers, so stage 1 is fine. But its output is always 0 or positive. The outer function f is the square root. Its domain requires the input to be 0 or positive. Since g of x is always non-negative, it always survives stage 2. So here the domain really is all real numbers. But now flip the order. Let g of x be the square root of x, and f of x be x squared. Let us derive the method from first principles. We want all x that make the composite f of g of x valid. First, x must be in the domain of the inner function g. Write down that set. Second, the output g of x must be in the domain of the outer function f. So we write an inequality, g of x must satisfy the domain condition of f. Solve that inequality for x. The domain of the composite is the overlap, the intersection, of the set from step 1 and the solution set from step 3. Let us apply this to a classic example. Let g of x be the square root of x minus 2, and f of x be 1 over x minus 5. Step 1. The inner square root requires x minus 2 greater than or equal to 0, so x greater than or equal to 2. Step 2. The outer function 1 over something requires that something not be 0. Let us solve a concrete problem. Find the domain of f of g of x where f of x is the square root of 4 minus x, and g of x is 1 over x minus 1. Step 1. The inner function g is a rational function. Its denominator x minus 1 cannot be 0, so x cannot equal 1. Step 2. The outer function f is a square root. Its input, which is g of x, must make for minus that input greater than or equal to 0. So we need for minus g of x greater than or equal to 0. Step 3. Substitute g of x. We get for minus 1 over x minus 1 greater than or equal to 0. Rearrange, for is greater than or equal to 1 over x minus 1. Now we must be careful. We cannot just multiply by x minus 1 without knowing its sign. We already know how to build a composite function. You feed an input into an inner function g, take its output, and feed that into an outer function f. Decomposing is simply the reverse. You are given a finished, complicated function h of x, and your job is to look at it and say, I can see this was built from two simpler functions. You name the inner one g and the outer one f, so that h of x equals f of g of x. Think of it like unwrapping a gift. The final wrap present is h. You peel off the outer wrapping to find f, and inside that you find the core gift, which is g. There is almost always more than one correct way to unwrap it, and that is perfectly fine. Why do we care about taking a function apart? Because in calculus, you will face the chain rule. The chain rule is the tool for finding the derivative, or the rate of change, of any composite function. It says, the derivative of f of g of x is the derivative of the outer function, evaluated at the inner function, multiplied by the derivative of the inner function. But you cannot even start the chain rule unless you can first look at a complicated expression and correctly identify what is the outer function and what is the inner function. Decomposition is that crucial first step. It turns a scary, tangled rate of change problem into two simple ones you already know how to solve. If you cannot spot the layers, the chain rule is just a formula you cannot use. So how do you actually do it? The trick is to think about the order of operations you would use to evaluate the function for a single number. Imagine you are a human calculator. For h of x equals the square root of x squared plus 1, what is the very last thing you do? You take the square root. That last operation is your outer function f. So f of something equals the square root of that something. Now, what did you take the square root of? The entire expression x squared plus 1. That whole chunk is the inner function g of x. So g of x equals x squared plus 1. You can always check your work by plugging g into f. F of g of x is the square root of g of x, which is the square root of x squared plus 1. That is exactly our original h. The last operation, a method, works like a charm. Let us see this in a real situation. Imagine you are blowing up a spherical balloon. The radius grows over time. Say the radius r equals 5t centimeters after t seconds. The volume of a sphere is v equals 4/3 pi r cubed. To get volume as a function of time, you compose them. V of t equals 4/3 pi times 5t quantity cubed. Now, suppose you want to know how fast the volume is growing at t equals 2 seconds. That is a derivative problem for a composite function. To use the chain rule, you must decompose it. Ask, what is the last operation? You cube the radius, then multiply by 4/3 pi. So the outer function f of r is 4/3 pi r cubed. The inner function g of t is 5t. The chain rule will then give the rate of change as the derivative of the outer volume formula with respect to r, times the derivative of the inner radius with respect to time. We already know that a function is like a machine. You put a number in, it does something, and a new number comes out. A composition is just connecting two machines in a row. The output of the first machine becomes the input of the second. Today we will see a real example. First we convert a Celsius temperature into Fahrenheit, and then we take that Fahrenheit value and compute the wind chill, how cold it actually feels on your skin when the wind is blowing. That two-step process is a composition. The Celsius temperature goes into the first machine, the Fahrenheit comes out, and that Fahrenheit immediately goes into the wind chill machine to give the final felt temperature. In real life, many processes are built in layers. A raw material goes through step 1, then step 2, and we care about the final result. But in calculus, we often want to know not just the final value, but how fast that final value changes when we tweak the very first input. If the Celsius temperature changes a little, how much does the wind chill change? That is a rate of change, a derivative, or of the whole chain. The chain rule tells us we can find that overall rate by simply multiplying the rate of the outer machine times the rate of the inner machine. It turns a complicated two-step problem into two easy one-step problems. This is one of the most powerful shortcuts in all of calculus, and it works precisely because we can see the process as a composition. Let us build the two machines. The inner function is the Celsius to Fahrenheit conversion. Fahrenheit equals 9/5 times Celsius plus 32. The outer function is the wind chill formula. For a given wind speed, say, a steady 15 miles per hour, the felt temperature W depends on the actual Fahrenheit temperature F. The formula looks messy, but we do not need to memorize it. We just need to see that it is a function, put Fahrenheit in, get wind chill out. Now, in calculus, the chain rule says the derivative of the whole composition, how wind chill changes as Celsius changes, is the derivative of the outer function with respect to Fahrenheit, multiplied by the derivative of the inner function with respect to Celsius. We take the rate of the wind chill machine and multiply it by the rate of the temperature conversion machine. That product is the overall rate. The messy formula breaks into two simpler derivatives we can handle separately. Let us work a concrete example. Suppose the air temperature is 10 degrees Celsius and the wind is blowing at a steady 15 miles per hour. First, we convert Fahrenheit equals 9/5 times 10 plus 32, which is 18 plus 32, giving 50 degrees Fahrenheit. Plugging 50 into the wind chill formula with a wind speed of 15 gives a felt temperature of about 44 degrees Fahrenheit. Now, what if the Celsius temperature rises just a little? The rate of the inner conversion is simply 9/5, or 1.8 Fahrenheit degrees per Celsius degree. The outer rate, how wind chill changes per Fahrenheit degree, we compute from the wind chill formula. At 15 miles per hour wind, that outer derivative is about 0.98. The chain rule says we multiply 1.8 times 0.98 equals about 1.76. So for every 1 degree Celsius the air warms up, the wind chill temperature rises by about 1.76 degrees Fahrenheit.